Okay. Looks like I figured it out. Not exactly how I planned for it to go, but we're here. So, trying a different software today. And as with anything, I tried to do as much experimenting as I could to make sure it was going to work. The only thing I could do that I hadn't already done was literally just start a stream, which is where we're at now. And that, of course, that becomes the final hiccup with everything. So hopefully everybody can hear me okay. If not, please let me know and make sure everything is coming through. All right. Yep. Okay. Thank you. Thank you. So it's it's crazy. I was looking at my YouTube studio yesterday and I realized that it's been almost 2 months. It was said 51 days as of yesterday since the last video upload. And I've done like my daily post things, but the the post upload, right, for the videos, those it just hit me. It's like, man, it goes to show kind of how things have been. Things have been crazy, guys. Let me just say that. Things have been absolutely nuts. And yeah, we're making the best of it, right? So, but nuts in a positive way. So, Chiller Academy is doing really well. I'm very excited about how things are going. Excited about the future. Really looking forward to getting this service course, or not course, but training launched. But anyway, today we are talking about centrifugal chillers and the questions you have around those. I do have one question already loaded up in the queue, and I see I've got a second one. Third one just rolled in. So yeah, let's get into this. So first question is, what are the pros and cons of a magnetic bearing chiller? Now, this is a very interesting topic, and as I think about it, it feels very similar to uh, a conversation around, say, like VRF, for example. There are there are pros and cons that really do have a heavy impact. Some of it is industry related to just the technicians ourselves, right? A lot of us really struggle understanding magnetic bearing chillers, and more specifically, I think the actual softwares we have to use in conjunction with them. And there's not only if we can get our hands on the software, but being able to effectively use that software. Ultimately, though, pros and cons. So, the major pros to magnetic bearings, it comes down to really improved efficiency. Um, and I think that's the main thing is we can significantly improve our efficiency and simplify the mechanical design of these compressors because most compressors we use in the industry are high speed. The way that we've had to achieve high speed in the past is through a geared system, right? Now, there are some modern motors that are DC based that are getting a high speed straight through the shaft, so those are a little different in modern terms, but for the most part, we had to do a bull and pinion gear to increase our speed on the drive shaft, on the output shaft for the impeller. It creates one, we have to have an oil system to keep those gears lubricated, in addition to the bearing system. And then those those gears become another friction point, another wear point. It further reduces the actual efficiency of a system. So by going to a mag bearing, now we're not limited by our bearing speed. Like so, journal bearings, for an example, or they can only we can only run those at such a high speed. Not only can we get the motor so high, but we have to be careful with how we use those, right? And by going direct to the shaft, we are able to reduce all of that extra mechanical friction and wear in the process. So that's one improvement for having a direct shaft system, which is arguably a very big improvement over a gear drive system for a high speed, right? Now, the big difference you have from going low speed to high speed is just the size of the compressor. With a high speed, you can use a smaller impeller. The whole package becomes much smaller in size to move that refrigerant. Versus with a low speed, you need a much larger impeller and system in order to get um, the same energy added to the refrigerant to create the lift and such we need. Another pro would be just completely removing oil from the equation. So while centrifugals don't directly mix oil into the refrigerant stream process, like it doesn't go through the impeller like it would a scroll or a screw. Like our discharge gas is not oil latent like some of those other compressors are, but it's not completely oil free either, especially if we have any kind of migration issues. And that's why we have eductors in the system to begin with. Is there is some oil that does get into the refrigerant stream, into the heat exchangers that we have to cycle around. That oil is just an insulator. We don't like it, reduces our ability to transfer heat. So by removing that oil from the equation, our ability to transfer improves. Our approaches are able to maintain even lower values, which means we have even better efficiency in the end. Um, so that is, uh, I think those are the two major things. Now, in terms of cons, I'm not even going to say, so some of the manufacturers are touting, improved life expectancy or things because of having no mechanical operation there for the bearings specifically, because the bearings historically are a failure point for oiled systems. My issue with that is honestly, mag bearings so far have not lasted a fraction of the time we would expect an oiled bearing to last. Now, there's a lot that has to play with that. We're still dealing with a fairly new technology. There's a lot going on around the development of mag bearing systems. Um, the these systems are extremely sensitive to electrical instability in a building in a space for that grid. So if you have a lot of instability, which a lot of buildings do, especially in major metros, I guess you don't have the cleanest power in the world. And unless we install some kind of isolation system on the front end of or coming into the chiller, whether it be isolation transformers or we install some kind of a bank, what do they call them, MCP or something. Anyway, unless we have that in place to where we're basically isolating the power the chiller is using from the grid's power, so all those instabilities and the static noise that tends to build up inside of a building with a lot of drive equipment, if we can eliminate that, that just wreaks havoc on all of our electrical control systems, which makes our life as the technician very difficult, and it reduces the actual life that we're seeing from these compressors. We're just not there yet, right? Will we probably be there one day where we've got all these things sorted out and like we have really good standards for moving forward? Absolutely. We're just not there yet. So I think that's something to just, that's one of the major drawbacks. And then our ability to work on it as technicians. There are plenty of us who have gotten enough training, gotten enough experience. Like we can service and work on magnetic bearings at this point, but there's a lot of us that really struggle to, and that's to be expected. Okay. These are not simple systems. You can break them down fairly well into their simple forms, but in the grand scale of things, especially if you're new to trying to get into this technology, it's it'll mess with your mind. Like it's a very very different animal, and so I think we should be mindful of that when we're working with younger techs who don't understand it as well as, like, so the rest of us have had an opportunity to get a grasp of the whole machine, and these younger guys, many times, you may be you're still trying to understand what the compressor does. Now you've got to understand this whole mag bearing thing on top of that, when you may not even fully understand how the oil bearings work correctly either. You're put in a pretty tough spot there, especially if you haven't had proper training on the subject. So anyway, yeah, I would say those are the major cons. Um, we haven't had very good results with bearing life. I just thought of another one I should add, but um, they're very, just very sensitive to the electrical grids. Technicians being able to work on them, not only having the software, but then knowing what to do with that software. And you've got to be very specific and precise, because it's like a turbo core, for example. If you don't do that bearing calibration just correct, I mean, just right, and you end up accidentally saving a bad calibration into that compressor, I mean, it can be fixed. Don't get me wrong, but it's a pain. Like, you dug yourself a hole there when you were actually better off with the first calibration you started with. But if you don't know the little tricks like unhooking the cable so there's no inputs and nothing else can disturb it and everything's just right, if you don't know some of that stuff, you get in trouble fast. A Well, I had another point I was going to make, and now I am. Oh, a really, really common thing. Actually, well, not using clean equipment and cylinders when doing mag bearing transfers. These systems cannot have oil. Now, some of the, say, more modern or I guess they're all modern. Some of the newest ones will have oil catches right in these suction cone, that if there is any oil in the system, it has a way of getting caught as it's coming into the compressor and trying to drain down into a little trap reservoir. That way but these are small reservoirs, if they even have one. And um, that's not, they're just trying to help solve for, that comes back to the technicians lack of practice and understanding. So people are, they're either retrofitting these into a system and they don't properly clean all the oil out, which is not an easy thing to do to begin with, or they end up charging dirty refrigerant, where maybe the cylinder got used on an oiled machine in the past and there was still some oil in the bottom of that, or some oil residue, something like that. And this happens all the freaking time. They turn around and charge that drum. It may be the same refrigerant that came out of there the first time, but now it's laced with oil, and then that oil gets into the bearing coils and just fries them. I mean, it does not take long. I get pictures sent to me all the time where the whole suction cover of the compressor is just full of oil, and you pull that front cover off, and just oil starts to drain out the front of the compressor. I mean, that just you cannot, that can't happen. And so that's a practice that we haven't properly adopted when we start working on these machines. We cannot have oil contaminated cylinders of any kind. And that is a major thing we have to take into account. And it is causing a lot of failures, more than just some of the natural failures that are happening on their own. So, anyway, there's your pros and cons to mag bearing. This technology is here to stay. People are only pushing it harder. Whether it's the right path or not, it's not really relevant at this point. It's the path we're on. Similar to VRF chillers, right? So it's just, this is where the industry is going. It's our responsibility to just keep up with what our customers need. And that means working on whatever equipment they have. And if that's what they have and we want to have their business, then we've got to learn how to do it. Anyway, good question though. Okay, so the next stuff loaded up here. Oops. Okay. Shrink this down a bit. So, can you discuss about pros and cons of a low pressure 514 and the 1233 versus 134, especially at low part loads below 40%? So, these are pure refrigerants. They're not blends, right? So if they were a blend, you know, that would be a problem. And there are, what is it, 454B, I believe, is one of the new blends coming out, or it's one of the, I guess, the only blend that I know of. Everything else, I think, are actually like R32 is pure, 514, 513, 1233, and 1234. They're all pure refrigerants. So the uh, just like with every refrigerant change we've seen, I don't expect much of a change with these refrigerants. Okay, um, I'm I haven't become an expert on these. Okay, so I can't say anything like crazy specific, other than they're a pure refrigerant, and I wouldn't expect anything dramatic to change. Now, what we can talk about other than just is the fact that it's gone from low pressure to high, or from high pressure to low pressure. Okay, so I think that is a good conversation there around this question, and maybe that's more of what you were seeking with that, than so much the refrigerants themselves. So low pressure, I'm actually a huge fan of low pressure personally. It does come with some challenges. So we've got a purge system, and we have, so now we operate in a vacuum, right? Especially our evaporator specifically, the condensers will fluctuate a little bit. So if we have, say, high condenser water and we've got enough load to maintain that, you'll have your condenser pressures get into the positive pressures, right? But your evaporator will almost always be in a vacuum. And when this machine is sitting still, most of the time it's in a vacuum. And every little leak just is adding non condensables into the chiller itself, which is where the purge unit comes into play. I'm very happy that we've gone with a ready purge style of system, which is basically, there's a few different ways we've done purges over the years. The old version we had with the YT, everybody hated. I don't think I've talked to one person that actually liked that purge system, but basically it used the oil system to assist with the purge function and pump out. With these systems, we actually have a separate pump out pump, and we've got an evaporator that a purge evaporator that we can basically, it's a shell. It's not a shell and tube, but it is a shell and coil, if you will. So the little purge unit has its own refrigerant circuit separate from the chiller, and then it is having its refrigerant flow through a little coil inside of that evaporator. The chiller's refrigerant, the low pressure refrigerant, flows on the outside of that coil, condenses down. So the refrigerant condenses, non condensables don't. They stack on the top of that little heat exchanger. And then as they stack up, we can use a few different methods to determine when it's time to kick on a pump out pump, which literally sucks that non condensables out of the machine and pumps it out into the atmosphere. So we can either use the evaporator pressure compared to condenser pressure. And when those get too far apart, that means we're stacking non condensables at a high enough concentration to need a pump out. Or another way it's done is we can monitor the suction line temp of the purge compressor, right? And as that temperature drops, that means we have less heat exchange uh, inside of our little evaporator, and then that means if our heat exchange drops, that means we have a lot of non-condensable stacking. Time for a pump out, right? So those are just some of the ways that we have gone about um, utilizing a purge system. So that is added to the machine, but for the most part, I this is just a preference thing. Okay, I have grown very fond of working with low pressures, and um, how they operate. I guess I'll say it that way. End of the day, short of the purge issue and the non-condensables issue, which separates it quite heavily from a high pressure machine, everything else is going to function just the same. We're still going to just base off of the same approach temperatures, the same saturation temperatures. We're still looking for the same leaving waters. We are the way we have to transfer refrigerant does change a bit, right? So when we get into the service side, the pumps we use for high pressure are not going to do as well as pumps with that as pumps designed for the low pressures, because the low pressures, because of their lower pressure, they do better with having a pump that has a higher CFM throughput through it. And that can be really difficult for these smaller pumps to do. Now, if you're working on a small low pressure, it's not that big a deal. But as that scales, your recovery machine and such, I guess it's that equipment can become kind of a challenge to do it efficiently, right? In order to not take absolutely forever to move that refrigerant around. Now, in getting into the part load, below 40%. Again, they're low pressure refrigerants. We've dealt with low pressure for a lot of years. Now, I say that. Okay, let me back up for a second. Those of us who have worked on train equipment in recent years. Now, I came up with a lot of fairly old equipment, so I have to take that into account. Like I worked on the YT, which was the low pressure York centrifugal before the YK. So I have a mindset of it's just low pressure, right? But I recognize there are quite a few people who have actually never worked on a low pressure. All you've seen is a high pressure. So a 134 machine, for example, or 22, something like that. You're going to troubleshoot it the same ultimately in terms of part load, load conditions and such. All of that is, from my perspective, it all ends up working out the same. I don't see major differences in how these machines function. All this is just the same principles still apply. The only variable is that purge unit and the non-condensables factor. That becomes a major factor with low pressure and it's stacking in the condenser. And that's something that we have to think about. So hopefully that answered your question sufficiently. If not, please feel free to either rephrase or ask further. And welcome everybody to the stream. Hope everybody's enjoying their day, enjoying their week. Yeah, making videos has been quite difficult recently. So I'm full head into Chiller Academy and I've got to stay there for a while still. So doing a stream like this is honestly at this point far easier than trying to do a recorded and edited video and make it something more than just a talking head staring at you, which quite a few people don't always care for. So we're just trying this out, seeing how it goes. I do want to put in here, this stream is sponsored by Compressor Solutions Group, CSG. They are based out of Houston, Texas. They've also got a shop in Fort Worth, and they've now recently got a shop in Ohio. And so they do screw and reciprocating remanufacturing. They also do the Invotech scroll lines if you're doing any kind of retrofits, and they can service on a national scale. Their headquarters is based here in Texas. They're really good friends of mine. I absolutely enjoy working with these guys. And they've opened up their shop. A lot of the training pictures and content that I have that I can show a lot of the internals of this stuff is from their shop. So if you're in the need of even just technical questions on compressors, right? You want to be able to call somebody and get some live support. That's not something I can currently offer as much as I would love to. They can help with that. And that's one of the huge things I love about working with CSG. They have a live support line. They're an amazing resource. So if you're working with a screw compressor of really any kind, They don't specialize in just one. They cover a very large variety between Train, Carlisle, which I guess Carrier, and York. Like they got you covered. So anyway, appreciate CSG Compressor Solutions Group. Jake Little's going to be your guy over there if you want to reach out, talk to anybody, and they'll be able to take care of you. So now that we're done with the sponsor piece of this, let's go to okay. So let's grab this one. 1 second. All right. So please explain purge suction high temperature. So I was kind of getting into this a little bit with the previous question, but to go a little further, so if you're dealing with a high suction temperature on a purge unit, uh, what that particular unit is looking for is it's monitoring the refrigerant temperature or the suction line specifically coming back from the purge unit evaporator. And actually, a high temperature, if everything is okay, right? So, if the purge unit is fully functional and accurate, then a high suction temperature is actually a good thing. That's what we want to see. That means that we have good heat exchange because the refrigerant coming from the condenser flowing through that purge evaporator is adding a lot of heat to the purge unit's refrigerant circuit. So as it's able to add that heat, a lot of superheat is added, and that condenser refrigerant is just condensing down into a liquid, the condenser gas to a liquid, and then gravity draining back into the condenser. So that is a good thing. Now there are some caveats to this. So one, if your purge unit circuit is having an issue, whether it be the metering device is not metering properly, the say the condenser coil or the condenser fan is having an issue, it's having a compressor issue, basically all the normal things you would have from a bad refrigeration circuit, right? Or if it's got, let's say, a low charge, right? Any of those things will can cause a underfeeding to the evaporator. And so if you're underfeeding the evaporator and you're not getting enough liquid in it, whether it's just not pumping enough through the compressor, we can't condense properly in the condenser for either the fan or the coil's dirty, or the metering device issue, right? So those things can cause a high suction. So if you're having a lot of high pressure and surging issues in the chiller itself, and it acts like it has non-condensables, which again, this is a low pressure machine. So if you're dealing with that, but yet your purge system is acting like it's all good, right? It doesn't have a problem. It's not seeing those non-condensables in its evaporator. Well, then you get into the conversation of, okay, well, is this purge system even functioning properly? I've had it several times before where just somebody who just didn't know any better went in, hooked up to the purge unit on the chiller I was working on at some point, and there's such tiny charge in there that unless you are going to replace that charge or you're servicing that purge, don't hook up a gauge to it, right? And so if you have to go as far as hooking up a gauge, just go ahead and plan to just start over, because just hooking even just a probe to it and taking it back off, that little bit of release can be enough on some of these purges to screw the whole thing. And so then it'll give you a low charge scenario. And I've had that happen before. Leak search the whole thing. The whole purge is perfectly fine otherwise. Give it a fresh charge and does great. No further issues from there, right? And it starts, the evap temperature starts to come down. Everything goes to work from there. So it's just something to, one of the things to consider, right? A really common one though is the suction temperature sensor itself could be failed or could have failed. So just be mindful of that, right? Verify that suction temp sensor, even if you take it off the line. Now, if it's one of those thread in styles where it's got the little threaded nut, those can be a pain. I've had those break a lot. Some guys have success with just retapping the threads on that little nut on the pipe. I personally have always kind of struggled with that. But the problem is the replacement sensors, the temperature is in the very tip of the sensor where the threads are. So you can't just strap it to the pipe thinking that's going to work very well, because in my experience, it hadn't. It usually reads a few degrees too high and it causes problems. So what I've had to do is literally like put the sensor at an angle, but have the tip still touch the pipe and kind of zip it all together and then insulate it with really well. That's worked for me. Anyway, so yes, high purge suction temperature could be these other conditions. But if you're not having surging issues, you're not having high pressure issues, and the purge is just running a high suction temperature, then you're probably good. Okay, it's cause to celebrate. You're low on condensables, if any at all, and things are just jiving away. That's what we want to see. It's when this suction purge temp plummets, that's when we know we've got a problem. Okay, and I do, by the way, as we go, so I had this whole idea of plans, so like we can dive into pictures and stuff. I've got a whole folder. So as y'all are asking questions, I'm hoping to have this finished by 12 my time. So it's 11:37 right now. But yeah, just keep it rolling, guys, and let me know what you think of this format as we go. So far, it feels like once I got it working, we're doing pretty good here. Oil pumps, VS, so VSOP. What is he saying? Oil pump. Here, let me. Yeah, you got a couple of. I might circle back. Let me make sure I'm covering more people. I have two. What is the ideal GPM for condenser water flow? So let's get this one loaded. Okay. So condenser water is typically, even for these, especially for a train with a CVH, usually around 3 GPM per ton. That is the primary target. If you're needing just kind of a on the spot ballpark, usually somewhere between 3 to 6 psid on most machines with the way Train does theirs is pretty close, right? You're in that realm if you're somewhere between 3 to 6 psid across the condenser barrel. Now that's just strictly a rule of thumb. Okay, that is not a hard set. They're all going to be this. Okay, now if you want to know that actual barrel's GPM, you can look up the condenser code via the model, and Train actually has a pretty good breakdown of their model nomenclature. So go look at that, and then pull up the engineering submittals. The engineering sheets for these CVHs. Okay, a Train does publish those similar to York, because they don't post these in their actual IOM manuals. So like Carrier, I see Carrier will post their flow charts in the actual IOMs, but York and Train I do not see do that. What they do is they put it in their engineering manuals, which are separate, and then you can pull that heat exchanger code from that from your model number, and then go to the manual, find that chart that shows that heat exchanger and your tube count, and once you have that code, you can then look at the flow curve and see what the GPM they're recommending is, and then typically they'll give you even some DP values that you can reference to know, okay, as we're designing this X GPM, we need this DP, something like that. So, like I said, the rule of thumb textbook answer, 3 GPM per ton. And in my experience, most of the time when I've ran these calculations or I've looked it up, majority of the machines, especially the smaller 450s, those are going to be around 3 to 6. You closer to 3 typically with the train. York, sometimes they'll run closer to the 6. Um, but yeah, that PSID difference just is if you just need a starting point, there's your starting point. Okay. So we have a R. Okay, yep. So yeah, that York question is going to be the same exact answer for that York one just below that, Jonathan. So York's the exact same thing. They've got the heat exchanger codes in the model number. Take that model number, look up the engineering manual for that machine. Now, if you've got, I would assume probably a YK. A YK is a 160 dot. Right now they're at 76. You could also look at a 54. So a 160.54 or 160.76 dash E1. That's the one you're looking for. So if you put that in, so, you could probably get away with just Google searching York YK engineering manual and you'll probably find it. But specifically, yeah, it should be 160.76 dash E1 as your engineering manual that's going to have the flow charts for that heat exchanger code. And then the heat exchanger codes are in the first part of the model number itself. So you'll have, the YK, you'll have the vintage, and then you'll start getting into the heat exchanger codes, and it'll roll through a series of different things. Let's see. I see my wife is in the chat here. Miss Natural Lioness there. Everybody say hi. Say hi, Lisa. Let's see. If a tube and major water enter a system, what process to use? So this is a good question. This is actually one of the procedures I am currently working on writing in the service training program. Let me get this one loaded up for y'all. Let's go here. Okay. Hopefully this little question thing, guys. One of the feedbacks I get on some of these I've done in the past, nobody can see the question. Hopefully this works. Okay. If a tube leak and major water entered our system, what is the process to use for dehydration? So, one, open the chiller up, let it all drain. We got to handle the refrigerant. So that's mostly a joke. We've got to get that contaminated refrigerant out of there. Granted, more than likely, when I've had this, what usually happens is the refrigerant, specifically if it's a high pressure, if it's a low pressure, not so much, but a high pressure, the refrigerant will push its way in because usually the refrigerant's at a higher pressure than your loop, not always, but usually. And so that'll force its way into the loop. You'll think you'll have a ton of air in the loop. You'll spend days trying to bleed it all. It's actually refrigerant that you're bleeding, not air. And after you get done with all the bleeding and you think you finally figured out, but you haven't figured out where the air came from, that's about the time you realize, oh snap, we had a condenser bust or evaporator bust, something like that, right? So once you mitigate the refrigerant, if you have any refrigerant in there at all, drain it down. Now, it depends on how long it's been able to sit in there. So how long of a span did it go? Some of these cases, I've seen it where they literally allowed the whole chiller to fill up to the compressor and it sat there for a period of time. By period of time, I mean weeks to months. Like there's been some of these cases I've seen where, yeah. So in that case, your only option is a full teardown. You're not going to get that machine back online. Not going to happen. So at that point, you go through a full teardown. You're going to overhaul that entire compressor. You're probably going to have to get into the heat exchangers and clean it up, and you've got a really, really difficult road ahead of you. And you need to bring people in who know how to do this. That would be your best next step. Now, let's say you caught it relatively quickly and you've got water in your heat exchanger. Things haven't been in there for very long, let's say hours to days at most. And now you responded quickly. Well, there is still some risk, but there's a chance that there's not extreme corrosion yet. So you're going to have to retube either way. Um, you're going to have to at minimum retube because you've got to do that to fix the leak. If you had a leak bad enough to cause that, I don't recommend just plugging the tubes. Now, if you caught the leak prior to the leak becoming it completely rupturing, where you say you caught it through an eddy current or something, then you can plug the actual holes, which is then getting a plug, putting some refrigerant sealer. So one I like in a case like that would be say 515. Put that on your plug, shove that into the tube on either side. I personally prefer to clear the line out of water as much as I can ahead of time, try to dehydrate it. So if it's not too bad, you can do that. Then you get stuck with mitigating what water got into it. So now we're talking about, say, a low pressure machine. Because if it was a high pressure, you would just be losing refrigerant, and you'd notice you have a low charge one day. You'd pull the end bells off, do some leak searching. Okay, we found this particular tube is the one leaking, but water hadn't made it into the chiller. If you have a low pressure, though, that's exactly what's going to happen. That water is going to start seeping in. Now, let's say this happened at a very small scale and you had that tube leak. It wasn't severe, but I noticed you did say major water leak. Okay, so we talking major, you're talking a retube and probably an overhaul. But for everybody else, what you can do is once you plug the tube and you've got a low pressure, it means you've got water in the system now. You're going to want to do a recovery and try to clean that refrigerant. And that means either doing an on-site recovery process. You could try to do a reclaim or let's see, not a reclaim. It'd be a recycling process on site. That'd be one option. Somebody like RefTech has some really good equipment to be able to do that on site. In some cases, like for myself, I've even gone to the point of let's just go ahead and replace this refrigerant. So we pulled it all out. Then we had to put the chiller through a dehydration process. And there's a couple of ways of doing that. You can either do a nitrogen purge to dehydrate that way, or you can use, say, like you can just do it through evacuation, doing triple evacs. And if you, depending on the scale of the machine, using a cold trap can be really, really beneficial. So a cold trap is a big cylinder that the vapors coming through the hoses go around the larger part of the cylinder, and then inside the cylinder we have another interior chamber that we fill with dry ice, and some people I've heard use antifreeze. Another one is denatured alcohol. Anyway, we'll fill that around with the dry ice, lock it all together, and what that does is instead of the all the moisture coming through into your pump and contaminating your pump very quickly, it collects there in the cold trap first, and it keeps the pump oil in a more pristine state, helps you get deeper, faster, longer, yada yada. So those are the two primary methods. I personally am a huge fan of a nitrogen purge. Okay, and this is something where you set your tanks up, you get a trickle purge going, you flow through the whole machine into the condenser. I usually go into the top of the condenser and then my liquid charging point at the bottom of the evaporator. I'll open that up, or I'll do vice versa, let it come back out the top of the condenser and come in. It just kind of depends on the circumstances. But by doing that and just doing a very slow trickle purge, almost like a brazing purge type of CFM. It's not a whole lot, but you do that for several hours with a tall 300 cubic tank, and that will That'll do a huge service to getting that machine really dehydrated, in addition to pulling an evacuation. So, anyway, to your point specifically, major leak, major water in the system. Um, my opinion, some people might tell you just plug the tube. I personally, like, if it's major, we're not talking just minor leak. If it's a major leak, we just need to go ahead and look at a retube. And if you're going to go as far as doing a retube, and if that water got up to that compressor, like genuinely filled the chiller, then I overhaul for sure. Like, I would really, really encourage that in a situation like that. Because part of the thing is, if you try to skip any of those things and then you try to turn it on anyway, you only make your overhaul situation way more expensive and worse. So not only are you likely to tear up more bearings, tear up your seals, tear up your impeller, you could also mess your motor up as well. Whereas with the state it's at, everything probably needs to be serviced and cleaned, but you may not have to have the motor rewound. Okay. You may not, some of your bearings may not be in that bad of condition. Doesn't mean you can't replace them, but you're not risking the impeller making any touchdowns anywhere it's not supposed to, and tearing the impeller up. And like, those are the consequences of, oh, let's just see what happens, right? And now your $100,000 overhaul turns into $150,000-$200,000 overhaul, if it's even worth overhauling, depending on how severe it is. So just things to consider. Okay, really good conversation going here. Let's see. Hey Ray, highly. Here we go. Discharge, superheat, minimum, maximum. Okay, I'll try to get. Let me see if I can get one more question in here. See, when it comes to brace fittings, starter pack for brass. On those brace fittings, in terms of a starter pack, no, I don't have anything specific. Troubleshooting purge unit by temperature approaches same as chiller. No. Okay, let's highlight this one. 1 second. Get this loaded up here. I have actually not used my, oops. I have not used my pictures near as much as I thought I would, guys. That's okay. All right. Troubleshoot purge unit by temperatures and approaches same as chiller itself. No, not really. So with a purge, my first go-to for most purge systems is, if it's having trouble, the first thing I'll do is, one, I'll perform a leak search. Let's see if I can even find anything. If it's got enough refrigerant in it to ice up at all, which most of the time, or a lot of times, they will, especially if they're having trouble. So if it's able to ice up at all, it probably has enough refrigerant in it to do a leak search. So I will start with doing a leak search with the refrigerant that's there. If that doesn't show anything, then the next thing I'll do is I'll just leave that refrigerant there. I'll add some nitrogen and go ahead and get that pressure up a little more. Be careful of the pressure ratings, okay? But then I'll do a higher pressure leak search to see if anything comes up that way. If I cannot find a leak, next thing I'll do is then I'll evacuate all that, pull it down, charge the recommended weight. Now, usually what I do is I'll go just maybe an ounce or so extra for me disconnecting. Okay, because I'd much rather have just a little bit too much than not quite enough charge in that system. And if the purge is still not functioning, where it's the evaporator's not pulling down, I know I've got non-condensables. I know I've got issues. I'm surging like crazy. I'm running high condenser approaches and pressures. So I know all that's happening, but the purge just ain't jiving. And I've got a fresh charge in there and it's still having trouble. Then I can I'll start looking into other factors such as what is my liquid line temp, what is my discharge temp, um, what are my suction temps doing, what is the temperature coming through the metering device, is the metering device metering. I should be able to isolate um, the refrigerant from the tubes from the condenser, from the chiller's condenser, not the purge unit, and see that suction temperature drop because I'm going to have very little load in that purge after a few minutes. So like there's some of those things I can do to try to troubleshoot the purge unit itself to see if it's a metering device or otherwise. Sometime or a very common one is the solenoid valves are very common to fail for the pump out side of it, and so those will start leaking atmosphere into them reverse flow, even though they're disengaged and closed, right? So that's just another point of it may not even be the refrigerant circuit itself. You may be drawing it through the actual solenoid valves that are meant to do the pump out phase of things. So that is my process. And yeah, in my opinion, you don't troubleshoot those the same way you would a regular little refrigeration unit or system. Granted, if you're used to working with small appliances, like that's something I did at one point in time, early on. Like you didn't hook up to those either. You took your temperatures, you looked at a lot of different variables without actually tampering with the refrigerant circuit itself. And that was always the worst case last thing you did scenario. But the approach values and stuff just don't quite line up the same for those. Okay, squeeze that one in. I think I've got one more here I can get in here before we got to go. Let's see, discharge superheat. Yeah, let's do this. This is a good one. Okay. All right, discharge superheat min and maximum. So in terms of a centrifugal, most of the time on the low end, if you've got, say, a low load or you've got, say you're running a higher refrigerant level in your evaporator, which is going to drop your discharge superheat a bit, you'll typically see, say, 10 to 15 degrees on the low end, right? So say you've got a lower load, or maybe you've got a little bit of a heavy charge, or if you're running your evaporator level a little high compared to maybe where it needs to be, and you've got some lower load conditions, then yeah, you take those factors into account. 10 to 15 on the very, very low end. Personally, I really don't like them to go below 15, even though depending on the compressor, some of them will. And by discharge superheat, I'm calculating that based off of the discharge line temperature from the condenser saturation temperature. Okay, so I'm taking those two, subtracting them, getting my discharge superheat. On the upper end, usually around 25 to 30 degrees with a pretty good load, charge and everything is good, you could see that. Now, if I've got a lower load condition, but yet I'm running a 25, 30 degree discharge superheat, I'm going to start asking questions, because that's that whole dilemma you fall into. Is, yeah, just because these are the parameters, right? These are your, say, min and max. So if I had to put a hard number to it, okay, 15 min, 30 max. I'll circle back around on the max here in a second, but there's just some hard numbers. Now, that is relative to the load on the machine. So it's a much more dynamic set of numbers. We have a lower load, but we're seeing those higher end numbers. That indicates that something may not be okay. We could be low on charge, or we may be underfeeding the evaporator, whether that be a metering device issue, a set point issue, depending on the style of chiller we have. So, or there could be a mechanical issue going on in the compressor itself, where something just ain't jiving right in there, and it's causing a lot of additional heat and friction. So these are some things to consider into what could elevate that discharge superheat, but yet you still have a low load condition. Lower load conditions means our compressor should be unloaded, and the discharge superheat should reflect that with a little bit of a lower discharge superheat. And then as we load up, we should see that superheat go up. Now, there are some machines that even with a pretty substantial load, they may still run 15 to 20 degrees of discharge superheat depending on how well they're tuned. And you won't see a whole lot of shift in that superheat from low load to high load. That just comes back to that machine, how well it was installed, how well it's configured, and just its operating conditions at the time. So if everything's jiving, like that, just because you've got a full load but you're running a lower discharge superheat, say 15 for example, doesn't mean you've got a problem. Okay, but it would definitely tell me that if I'm on the low end of the load but I'm still having a high discharge superheat, that would make me want to ask questions. I hope that makes sense. This is where we have to apply our human logic and our understanding and experience of these things, because the circumstances are very dynamic in what could or couldn't be. Okay, but that's why you are paid to be in the role that you're in, and that's why we're doing a conversation like this to help kind of build on these things and get you a better foundation. Now, the dangerous parts of so the 30 degrees, there are some situations, especially at really high peak loads, you might see more than 30. For a lot of compressors, it's probably not going to be that big a deal, especially if you have that high load. So just because you've got over 30 doesn't necessarily mean freak out. Or start trying to dive in and chase ghosts that aren't really there. Like that's the big thing that gets a lot of us. We start chasing ghosts, trying to see what's going on. In reality, everything's fine. It's just in a specific circumstance, right? So now, if I'm below 10, something's wrong. Something is wrong as far as I'm concerned, and I'm going to start looking at where that liquid level is first and foremost in that evaporator, and whether it be an overcharge, whether it be, say, overfeeding, we could have a metering device issue. There's a few things, but when you start getting below that and the closer you get to 5 and less, especially, that's when you start getting into that liquid droplet territory, and that's when you start shredding impellers, because then that refrigerant level can get so high. We're only running a half a degree to 1 or 2 degrees of suction superheat to begin with. And these compressors cannot do liquid, period. Okay. So a droplet of liquid is a rock thrown into that impeller, and it will ding it, it will mark it up, and it will just completely destroy that aluminum, especially these high speed machines that are running, 20 to 40,000 RPM. Not going to work. So that is a condition that we really, really have to be mindful of. And I'd much rather run high discharge superheat than run a low one any day of the week. Okay. Whew. That was fun. All right. I don't have time for questions, but I would love to hear some feedback on just what do y'all think of this format? And I'm thinking about trying something like this on a weekly basis. So, for example, whether it be Monday or just picking a day next week and doing another stream then similar to this. I'd be very curious to hear your input. Hopefully, I can spend some more time with this software and figure out why it's not working. We will get that worked out. And yeah, like I said, this is far more less time intensive to do this, and I'd rather come hang out anyway. I don't get to hang out with people as much anymore. Like, I'm focused on Chiller Academy. This is what I'm doing. This is everything. And so getting to come in, have a conversation, have an open chat about stuff, like, this is really fun. So I will end up posting another poll in the community to where we can kind of work through the next topic selection. A couple of topics I'm looking at for this next time would be one, the future of VRF chillers was actually pretty highly voted on, but Centrifugal Q&A did win out. So that'll probably go up again as an option. Doing a conversation on the new Copeland, what they call it, the Aero Lift centrifugal, the new Copeland centrifugal they just come out with. I did a full deep dive on that compressor, the technology they're using. I've got a lot of thoughts. So yeah, we can, so that'll be probably one of them is, hey, do we want to do a conversation around that compressor? Maybe. And then I'll figure out some of the others, but yeah, be looking for that community post coming up. If you're not already in Chiller Academy, I'd really encourage you to go check it out. Just think about it, right? This is what I do full time. I've committed. I've stepped out of the field, committed my career to this going forward. This is what I've always wanted to do, and to be able to educate, help others, and grow, and help this industry take steps forward. So chilleracademy.com. Like I'd love to be able to work with you over there. We've got a community page. All the lessons have a comment section. That's what I spend a lot of my day doing. If I'm not working on the lesson material itself, then I am in the comments and I'm trying to respond to those as fast as I can, in addition to helping you through email and otherwise. So love to be able to work with you. For all of those that are in the academy, y'all are doing some great work out there. Keep it up. I really appreciate the support and the feedback that you've given. And yeah, any final thoughts? And I think the microphone ended up being a bit quiet. Again, that's going back to the software issue. But yeah, with that, I appreciate everybody. Thank you.